A lot to do. So today what I want to do is cover a lot of the systematics that you can use in doing mathematical derivations in thermodynamics. I think, as I mentioned in the last lecture, when I used to work through thermodynamics, I felt it was a bit of a random walk, substituting whatever equations I found that related the relevant quantities. What I'm going to try to work to today is that there's actually quite a bit of systematics in how you transform differentials that you don't know into quantities that you do know. So let me recap where we were. In the last few lectures, we've defined thermodynamic potentials, things like enthalpy and Gibbs free energy and Helmholtz free energy. But we also defined general Legendre transforms. And by now you should know what these Legendre transforms mean with respect to equilibrium and how you set them up for a given condition. And again, what you should think about is that the condition is the boundary condition, right, is defined by the extensive variables. So all you need to pay attention to is which extensive variables are constant and which extensive variables are not constant. And the extensive variables that are not constant, you Legendre transform with respect to these. And as I've pointed out, the reason you're doing that is because you're optimizing not just the energy of the system, but the energy of the system plus its potential in that environment in which that extensive variable can change. So, for example, we do an example of some Legendre transform that we have not done. Let's say I have a material that's an oxide, and I anneal it at very high temperature. So I would anneal it in some partial pressure of oxygen. So when I anneal that system in a high temperature environment where I have a certain PO2, that material is considered open with respect to oxygen content. So the state I would find is not the state with minimal Gibbs free energy. It would be the state with minimal whatever, and whatever would be the Legendre transform of the Gibbs free energy with respect to the extensive variable that gives the amount of oxygen, right? So there's an extensive variable that you could say it's the amount of oxygen. To that corresponds a chemical potential of oxygen, which is its conjugate. So what I would define as a potential, phi, is G minus mu naught O naught, right? Where the O stands for oxygen. So rather than using Gibbs free energy, this, as it's called, this is called a grand canonical potential. Usually grand canonical reflects systems that are open. This thermodynamic potential is the one you would optimize to find equilibrium in open boundary conditions. We also started defining sort of basic mathematical relations, and what I got to the last time was the Maxwell relations. And what I show you is that they have a general structure, the Maxwell relations, that it's always looks like dx dy, keeping the conjugate of x constant, and this is equal to plus or minus the conjugate of y, the conjugate of x, keeping the conjugate of y constant, so that's y. And if you like to convince yourself of that relation, then you just rederive the differential where this comes from, and it has to come from a differential in which the variations are variations of y and x and conjugate of x. So it has to be a potential with that as its natural variables. I want to go through a few other relations. Just to go faster, I've put them on the lecture notes. Let me just share that with you. Okay, so a few other handy relations that we'd like to use is something that mathematicians don't often like you to do, but if you have a partial derivative, df dx, that's of course equal to 1 over dx df, right? And the reason is that a partial derivative is really nothing more than the ratio of two differentials. So if I invert that ratio, I get the inverse. And again, this is really only not true when you have discontinuities or when you have divergences. The second one is the chain rule. And we'll see later how we typically use that to change extensive or intensive variables and disposition. So if you have a function u that's a function of x and y, then df dx at constant y, you can now write that as a derivative df du times du dx, all at constant y, okay? And the one we'll use a lot is called the cyclic rule. Which state that if you take the three permutations, right, of if f is a function of x and y, and you take the three permutations df dx at constant y times dx dy at constant f times dy df at constant x, it's -1. Okay. Note the structure of the cyclic rule, right? That there are different things being held constant here. If I had the same thing being held constant, then I could just cancel the differentials, right? And then this would be 1. So what I did was not correct, right? Because these here are variations. These variations, for example, this df and this df are with constant, a different variable constant. I'm not going to prove to you that's in several of the reading notes I've given to you, but if you want to start proving this, you would start by writing out what the differential of f is in terms of the differential of dx, in terms of the differential of dy, and then from that you can fairly easily derive the cyclic rule. Okay. Let me stop sharing now. Okay, and go back. So, having said that, I want to do a basic example. I'm going to take a wire, so could be a metal wire, but doesn't really have to be, but for the sake of argument, we could. That I'm going to apply a force to rapidly. And I'm going to do it rapidly so that this is, that as I elongate the wire, and I'm going to elongate it only in the elastic regime, so we don't have internal energy dissipation, so not in the plastic regime. So I'm going to do an elastic and adiabatic pull, so application of force. And that will ensure that whatever happens in the wire is isentropic, right? Because I'm doing it elastic, so reversibly, and I'm doing it adiabatically, so it will be isentropic. And I have a poll for you. I think I can launch it. My question to you, which I would normally ask in classes, let's see if I can do this. Does the temperature of the wire go up or down? Or does it stay the same? So how about you try to think about that, where it goes up, down, or it stays the same? It's always good to, with these problems, to think about the effect of what's going on and the sign of what you would expect. After that, you can put math on and the numbers, right? You know my theory about signs in final results? If you have 5 steps in an equation, and each time you get you have only 90% chance of getting the sign right, you know what the probability is that you get the sign right at the end, right? You're starting to hit 50% or lower, so. Okay, there's only a few of us today. Okay, most people think that the temperature of the wire is going to increase. Some people think it's going to stay the same, and we have about a third of people who think it's going to decrease. Okay, let's see what happens. This is why you know thermodynamics, right? Okay, let's see what happens. So, what is it we want to know? So the first part of a problem like this is, can I write my question in terms of a partial derivative that I need to know? And then can I reduce that to quantities that I know? Well, if you think of this literally, what I'm asking for is, do I know what dt, df is at constant entropy? Really? Right? I'm asking how the temperature changes as I apply force, and I do this at constant entropy. So our job now is to figure out, can we turn this into quantities that we know? So you look at that and first you go like, well, how could I reduce that? So first of all, is this Maxwell bait? I call Maxwell bait if you could transform it through a Maxwell relation. And it is, right? Because I'm taking a derivative of t and I'm keeping s constant. So the question is that useful? So to check if it's useful, you can right away write out that this would be equal to plus or minus the L ds at constant f, right? That would be the Maxwell relation. I don't really care about the plus or minus sign for now, but to me that doesn't look very useful. I really have no idea how linked changes with entropy. So, and the reason is that we don't know any physical quantities at constant entropy. We usually know them at constant temperature or at constant pressure. We don't know them at constant entropy. So the way you do that is by using the cyclic rule, right? The cyclic rule is essentially a way of permuting the position of all the variables in your partial differential. So if I use the cyclic rule, s is going to appear sometimes in the numerator, sometimes in the denominator, and I'm going to get rid of it. So let's do that. So I'm going to use the cyclic rule. So then this becomes equal to minus ds df at constant t divided by ds dt at constant f. And now we're in much better shape, right? Because we already have something that we recognize. A temperature derivative of entropy is a heat capacity. So this is going to be something like heat capacity under constant force. So specifically, this will be, I'll call it Cf divided by T, right? Because to have heat capacity, you would have to have a T in front of here. So that term we already have. So what do we do with this term? Again, is this Maxwell bait? It is, right? Because you're taking a derivative of the entropy with respect to temperature. So I could transform that. So what would that become? You don't even have to write it out, right? I would have the conjugate of F, which is L, conjugate of S, which is T. So this is going to look something like plus or minus the L dt. Right? At constant force. And that looks like something we recognize, right? This is thermal expansion. It's linear thermal expansion, not volumetric thermal expansion. But if I define the linear thermal expansion as 1 over L dL dt at constant, in this case, constant force, and the force would be 0, then this is going to relate to linear thermal expansion. Now, if I want to know what the sign is, again, after a while you'll get good at this, but if I want to know what the sign is, well, this has to come from a differential of a function with t and f as natural variables. So what would that function be? So let's kind of work that out in detail. Most of the time you'll skip this. So we need something that's a function of f and t. Well, f and t are both intensive variables. So that means that we have to define some free energy, which is a Legendre transform of the internal energy, which is U minus Ts in this case, minus Fl. Right? Because the internal energy would only be a function of the extensive variable, so I have to Legendre transform twice. So what I would do is I would work out what the differential is, which by now I know you know how to do well, is minus S dt minus L df. And now if you take the Maxwell relation, you would find that the S df at constant t is equal to, and I got two minus signs that give me a plus sign, would be equal to the L dt at constant f. Okay, so basically we have the plus sign here. So let me bring this to the other board. I hope you caught everything on that board. You know, if you missed something, just tell me, okay? I'll be happy to go back to that board. Or I can copy it on the next board I start. It's a little tricky here to work with these boards and have the camera track me. Okay, so if we retake everything, we now get what our differential is. dt df at constant s is minus dl dt at constant f divided by cf over t. So this is minus L times the linear thermal expansion times T divided by CF. I can stop here or I can keep on going. Most things I know, thermal expansion I would know typically. This is a slightly strange heat capacity, CF. So it's neither CP nor CV. It's the heat capacity under a constant one-dimensional force, right? Not a three-dimensional like pressure. So if you really wanted to work hard, you could work this out. But in many cases, we know that CP and CV for solids is very similar to each other. And so I'm just going to assume that for the materials I work with, this is equal to CP. So if I now do a finite integration here, I'm just going to assume that I do small changes in T and F. I can estimate what delta T is. Delta T is going to be, well, the increase in force, which I'll write as area, times the increase in stress. And then I have L, then I have alpha L, then I have, then I have T, and I divide by CF. And something happens that very often happens, is that I get the volume to show up, right? Because I have area and L, this is the volume. It's because I went to stress here. Let me give you some real numbers. Let's say I take iron. So for iron, I'm going to assume that CF is equal to CP, and CP at room temperature would be about 25 joules per mole per Kelvin, approximately. The linear thermal expansion for a lot of materials is order 10 to the minus 5, 10 to the minus 6. Here it's 11.8 times 10 to the minus 6 per Kelvin. The molar volume of iron is 7.1 times 10 to the minus 6 meters cubed per mole. And then I assumed a typical elastic stress So how much stress shall we apply? I sort of thought on a metal, I'll apply something like 100 megapascal, which for many metals is in the elastic regime. Of course, this is a choice I make, right? How much stress I apply. So let's set this to 100 megapascal. And if I plug all that in and get all the units right, I would find that delta T is about minus 0.1 Kelvin. So it's pretty small, right? So who was right? Well, I guess you were kind of all correct, right? That because I hadn't told you what the thermal expansion was. So what you see is that, sorry, I forgot a minus sign here. There's a minus sign in front here. So for most materials with a positive thermal expansion, the temperature drop is negative. But of course, there are materials with negative thermal expansion like rubber, right? And for rubber, you know this, right? People do this experiment all the time. If you take rubber and you sort of stretch it quickly, its temperature actually goes up, and there the effect is much more pronounced because the thermal expansion is much larger. But in general, the temperature actually drops. So that seems counterintuitive, but if we look at where this comes from, you can actually go back to here, right? So right away when we did the Cyclic Rule, you know that the SDT is going to be positive, right? Because it's a heat capacity. So all depends on the SDF. And let me write that slightly differently for you, just to make sense of the sign. I could write the F as the SDL at constant T times the LDF at constant T, right? That's the chain rule. And this allows you to see things a little more clearly, because the LDF has to be a positive quantity, right? It's sort of like compressibility. If I pull on something, the length has to get bigger, right? So this has to be a positive quantity. So the question is, what happens to the SDL? So, and what's the question here? We're asking, what happens to the entropy of a material when I make its length bigger, or in 3 dimensions, it would be when I make its volume bigger. And it turns out that what you can see here is that this is actually the source of thermal expansion, right? What happens to this entropy derivative? So for most materials, if you make the volume bigger, the bonds get softer, they vibrate more, they disorder more, you get higher entropy. But as many of you have seen before, for a few materials, that's actually different. And polymers and rubbers are, for example, in that category. There, if you stretch them more, their entropy goes down. And we'll come back to that example, maybe later in the lecture, or probably at the next lecture. So what's really happening here is, right, that the system has to compensate for the entropy going up by the application of the force. It has to drop the temperature to keep the total entropy the same, because this is an adiabatic reversible pull, so it is at 0 entropy change, right? So the bigger length wants to make the entropy go up. So the only way the system can compensate is by dropping the temperature, which makes the entropy go down. And in some sense, this here is a statement of the fact that these balance, right? That the temperature drop is the one that exactly makes the entropy change balance. So I'm going to give you a puzzling example that I think only thermodynamics can answer. And we can either come back to it in next lecture, or you can do it in discussion. And this is a real practical problem in MEMS, right? So let's say you have a cantilever. So it's attached to something that's rigid. And this is sort of like a very small scale cantilever, right? Could be less than a micron. And I make the cantilever vibrate. So like, you know, I wouldn't be my finger at the tip if it's a MEMS cantilever, but you know what I'm doing, right? I'm making it resonate. And this thing is in vacuum. And some people used to think that the cantilever is essentially, since it has no friction with air, can resonate forever. Because it has no energy dissipation mechanism. If you think of this as purely mechanics, it has no energy dissipation mechanism. But if you think of thermodynamics, it does have an energy dissipation mechanism, right? Because what happens when the cantilever is bent? So as it's cycling, at some point, I'm exaggerating, it's bent here, right? When it's bent, I have stresses in the cantilever, which are sort of compressive here and tensile on the outside of the cantilever. And what we just shown is that that creates a temperature gradient. So part of the cantilever, one side is going to be higher temperature than the other side. That means that heat's going to flow. That means that you're going to have energy dissipation. Anyway, think through this, right? It's kind of a cool example how the mixing of temperature and mechanics here really creates something that maybe you wouldn't have thought about before. But I guess we sort of solved it right now. Okay. I'm going to walk you now through the general, I would say, I wouldn't call them rules to derivation, but guidelines or things that might help you to see a bit, I don't know, the trees through the forest or the forest through the trees. If you have thermodynamic potentials in derivatives that you need to reduce, you want to always bring these to the numerator. So you always want to bring thermodynamic potentials to the numerator. And you want to eliminate them with their differential. So basically you substitute in their differential. And the reason is that their differential contains variations of typically physical properties. So let me give you an example. If I asked you to calculate dt dp at constant enthalpy, remember this is the Joule-Thomson expansion, right? We ran something through this valve. We decided that it had to be constant enthalpy, and we asked what's the change of temperature with pressure. So if I follow my own guideline, I want to get rid of H being held constant, right? Because it's not something I can work with. So I bring it to the numerator by using the cyclic rule. So this would be equal to the H dp at constant T divided by the H dt at constant P. And then I would plug in what H is, right? dH is TdS plus VdP. So if I plug that in, don't try to do fancy derivatives, right? dH is a differential. This dH is a differential. All you do is stick it in, right? A differential is not the same as a derivative, right? So this is equal to minus T ds dp at constant t. And then I get v dp divided by dp, so that's just v, right? Divided by, now I take it at constant p, so the second differential goes away. So I just get t ds dt at constant p. And I've struck pay dirt already, right? I'm not going to do it yet, we'll do it later, but you know, you right away see a heat capacity show up, right? This is going to be a heat capacity, and if you're fast, you see what this is going to become, right? This is going to become Maxwell bait, right? It's going to be dV dt, so it's going to become thermal expansion. So I'm done, right? But formally, I'm going to do that in the next step. So the second thing you do is really part almost of the first step, is that you always bring S to the numerator. And there are typically three operations that you do on that. You turn it into heat capacities if you can. So if you have a temperature derivative, right, you turn into heat capacity. Or you use Maxwell relations on it. So this would be or. And sometimes that's Maxwell plus chain rule. I'll give you an example of that later. So go back to our example here. T ds dt, we don't have to do anything about that. That is Cp. So this friend here is eliminated. And the second one, the SDP at constant t, that's Maxwell bait, right? So that is dV dt at constant p, right? Plus or minus. And it's minus, which I'm not going to derive for you anymore. So this is equal to minus V times alpha V, right? This is the thermal expansion. So now I've taken the whole Joule-Thomson differential and I've reduced it to things that I know. So if with these two steps together, I find that this is equal to V times T alpha V minus 1 divided by Cp, right? Completely logical derivation, I like to think. Remember that we proved that for an ideal gas, this was 0. When we actually did the Joule-Thomson expansion in the beginning, we only knew ideal gases, so there we found that that's 0. So try to show that this expression reduces to 0 for an ideal gas. And you would do that by plugging in what alpha V is for an ideal gas, right? By formally taking that derivative. Okay, so these are the two important steps typically in derivations. Sometimes there's some more work to do, and sometimes you also bring volume or any other extensive quantity in general to the numerator. And you turn into derivatives of T and P, or in general, T and the conjugate of the extensive quantity. And then 4, which we almost never do, unless I explicitly ask you, is you turn heat capacities into things you know. You turn them into CV and CP plus other things. Usually there are correction terms to it. There's sort of a fifth one that I haven't given previous years, but one of you asked me about it. So if I have a derivative ds dx, where x is an extensive quantity at constant t, if I use Maxwell on this, you're going to get dy, which is the conjugate, the intensive quantity dt, right? At constant x. That's usually not useful because you always measure the temperature dependence of extensive quantities like volume, magnetization. You don't measure the temperature dependence of intensive quantities. So in that case, so when you have the entropy derivative of an extensive quantity, it's so much easier to use the chain rule first. So you get ds dy at constant t times dy dx at constant t. And why is that? Because this will transform by Maxwell into dx dt at constant y. So imagine x is any extensive quantity, right? So examples of this are, dv dt, dm dt, right? Things that are normally measurable. And then what is this? This is the relation between, I'm going to invert it. It's actually easier if you see it as dx dy. So this derivative is also 1 over dx dy. So what is dx dy in general? Right? That's typically specifically to a field, right? So if I put volume and pressure here, that's compressibility. If I put strain and stress here, then that's a part of the elastic tensor. If I put magnetization and applied magnetic field here, then that's susceptibility, right? So the relation of an extensive variable with its conjugate tends to be specific to a field, and you've seen these quantities from other fields already. Okay? So this is kind of how you do derivations. I can't guarantee you that there's never a more creative step that you need to take, but this will, in general, get you through, I would say, 80% of what you need to do when you take derivations, okay? So what you have now is the basic math to set up grand potentials, to set up equilibrium, and to, more importantly, relate behavior in those boundary conditions to more classic behavior, right? So you can relate now dt dp at constant enthalpy, maybe how dt dp would happen under constant volume. So let's do a few examples. Actually, let's do a bunch of examples to let this sink in. First, I'm going to prove something that we left hanging in an earlier lecture. I'm going to prove that du dv for an ideal gas, so du dv at constant temperature is 0 for ideal gas. Okay, so if I follow my own rules here, what do? I plug in what du is. So this partial derivative is equal to t ds dv at constant t minus p. And the reason is, of course, that du is t ds minus P dV. This is Maxwell bait, right? So this is equal to dP dt at constant V. And for an ideal gas, I can calculate that, right? Because I have PVs and RT. I have a relation between these three variables. So P is nRT divided by V. So dP dt at constant V is equal to nR over V. So if I plug that in here, I have that I have T times nR over V, that was what the partial was, minus P. This here is P again, right? So this is equal to 0. So we've proven, whereas in the beginning we had to make that part of the definition of an ideal gas, we have now proven that for an ideal gas, the energy does not depend on volume, the internal energy, which is a fairly remarkable statement. But later we'll make, in statistical mechanics, we'll make a physical model of the ideal gas. And because that model will be one of non-interacting molecules. And so if the molecules don't interact, it essentially doesn't matter how far they are away from each other. So there is no volume dependence on the internal energy. Okay, you're still with me? This is a perfect Monday morning lecture. You're still all very fresh from the great weekend. Ready to take on the world and the math of thermo. There is one more relation that I'm not going to prove, but is in Zemansky. It's also, to be honest, in Lafontaine and in Callan, but in Zemansky it's page 260, 261. But I really recommend you try to prove it yourself for the sport. It's the relation between two partial derivatives when you hold different things constant. So here I'm taking dx df at constant z, and I want to know how that relates to dx df at constant y, right? Well, it turns out the correction terms make some sense when you think about it. It's how dx changes with y at constant f times how y, I need to be a little careful here. These are lowercase y's, not that it matters, but these are y's, this is an f, times dy df at constant z. This is quite useful because very often we will measure a property under one condition and we will want to know it under another one, or vice versa. Maybe we measure it under this condition, we want to know it under another condition. What's the correction term? So an obvious way to use this is to study the difference between Cp and Cv. But we'll do some much cooler stuff later. But the classic one is to calculate the difference Cp minus Cv, because as you know, these are entropy derivatives. So this is T ds dt under constant pressure minus T ds dt under constant volume. So that means that Cp, Cv, I'm going to bring the T over to here, so I don't have to carry it around there, is this difference in entropy, derivatives, ds dt at constant p minus ds dt at constant v. And now let's apply this relation to it. The difference is going to be how S changes with volume at constant T times how volume changes with temperature at constant P. You should spend some time looking at this because this actually makes sense, right? Here I want to take the S dt at constant P. First I take it at constant V, right? But then to get back to constant P, I need to know how volume changes at constant P and then multiply that with how the entropy would have changed with that volume change. So look a little through it, that it actually makes some physical sense. Okay, so what is this equal to? This here is going to be easy, right? Obviously a thermal expansion is showing up here. Right, there's going to be V alpha V here. And what do we do with this? Again, this is Maxwell bait, but remember what I said, you're taking the derivative of entropy with respect to an extensive variable. It's much easier if you use the chain rule on that and you turn that into the intensive variable. Because this, through a Maxwell relation, will give you another thermal expansion. Right? This is going to give me, this guy here is going to give me dV dt. So this is going to give me dV dt at constant P. And then what is this here? This is the inverse compressibility, right? I have dP dV, so that's 1 over dV dP, right? You should learn to start recognizing these things, right? I have some derivative that partial derivative that relates a conjugate pair, right? dV dP, dP dV, the m dH, the E dP, all these things I know, right? So somewhere the compressibility is going to show up in here. So if I put this all together, Cp minus Cv divided by T is equal to V times alpha V squared divided by the compressibility, beta T. Now you see that there was some issue with our argument we made in the first lecture. When, remember in the first lecture I made you do this intuitive argument arguing why Cp is larger than Cv, but it only worked for positive thermal expansion. Now you see that it always works, right? Because the thermal expansion appears squared here. And that means that the term here is always positive because volume is positive, thermal expansion is positive, and beta T is positive. So Cp is always larger than Cv, even for materials with negative thermal expansion. If you dig very deeply, it's because for materials with negative thermal expansion, the entropy behaves differently. The entropy change, how the entropy changes with length has the opposite sign as well. And that's essentially what causes the cancellation. So there are many questions that you can ask in the same vein. So let's say I asked you, so this is a question, is a material stiffer under rapid compression, so adiabatic compression, than under isothermal compression? Oh, we should have done a poll. So rapid So this is a very relevant question, right? So, by the way, rapid in thermodynamics often means adiabatic, right? So there's a limit where you do any process so rapidly that even if it wants to change the temperature, it doesn't have enough time to do heat flow, heat exchange with the environment. So we define that limit as adiabatic. So again, this is very relevant. Let's say you take a material and do shock compression within the elastic regime. So shock compression can be so fast that you don't have heat exchange. So the question is the compressibility modulus under isentropic conditions, which is adiabatic, reversible, is this less than or equal to the volumetric compressibility that we know, which is the isothermal one? So that's the question, right? What do you think? Well, I guess this is good news, right? If you can't come up with it by thinking, then there's some use of thermodynamics for you, right? To actually derive it. So I'm going to let you derive it, but I'm going to give you what the answer is. So again, so these are volume derivatives with pressure, right? So what we would be asking here is let's calculate beta S minus beta T, right? So that would be minus 1 over the volume times dV dP at constant S minus dV dP at constant T. Right, this is the regular compressibility. What you will find if you do that reduction of derivatives is that beta S equals beta T minus TV, the normalized volume, times the thermal expansion squared divided by Cp. This here, again, is a positive number, right? All the quantities are positive. You're subtracting it from beta T. So the result is that beta S is less than beta T. So it is less easy to compress a solid. Okay, now I'm confused. It is less easy to compress it isothermally, adiabatically, right? Because this is less than that, but there's a negative sign here, so this here is greater than that. That seems to be the opposite. I know that that's the right answer. Okay. Yeah, so the volume change is less when you do an adiabatic compression. So the material is stiffer when it's adiabatic than when it's isentropic, isothermal. Okay, should move on before I get myself in trouble. We left a paper on Piazza about some research work that I did maybe 10 years ago. Sort of, you don't have to, it's not required reading at all. It's really for your interest, but to sort of show you that thermodynamics is relevant on occasion. if you know how to apply it. And the problem we were studying was decohesion or fracture mechanics under the influence of chemistry. And in particular, intergranular fracture, which I'll simplify here. Let's say you have two grains of a material, grain 1 and grain 2. And the decohesion law for grains is defined like the force or stress relation versus the separation of the boundary. Like, you can call this delta L, right? So just like an elastic problem, I pull the grains apart. What's the force I need to pull them apart? And typically that looks something like this. As a function of delta L, in the beginning, you the force rises, right? You're trying to pull bonding apart. There's some maximum where your where your system starts to pull apart, and then if you actually were to sort of mechanically constrain it, you would be able to follow this, and this would go down, right? So there's a point of maximum force. So the interesting question that has come up often in research, what happens when you do this slowly? Slowly with respect to chemical degrees of freedom. So let's say you have something like hydrogen sitting around in a material. So you're particularly thinking of something like hydrogen embrittlement. I could derive this derivative, df dl. At the boundary, I could derive it under constant amount of hydrogen. So, hydrogen segregates to this boundary to some extent. And there's a whole debate whether that makes it stronger or weaker. That's not the point now. But if I do this slowly, that's not the correct derivative. Because if I do this slowly, then hydrogen equilibrates with the boundary at any position of L. So what I really want is the boundary relation df dl at constant chemical potential of hydrogen, right? So if I think of my boundary here as a thermodynamic system, if I do this slowly, this pulling, hydrogen can flow in or out. Because, if the boundary is slightly more separated or less, it's going to want a different hydrogen content. So this is the relevant derivative. Well, it turns out that, you can sort of do a rough calculation what that is, and that's what the paper's about. But again, the paper's sort of for your general interest. It turns out that this looks fundamentally different. This relation, if you plot it now as a function of L, it looks like this. In the beginning, it's the same because nothing happens. And then it does this. It crosses over and it goes down. And so what does this look like, right? This looks like a phase transition because you have a discontinuity in an extensive quantity. We'll talk about that a bit later. But this is not the kind of thing you could intuitively see. Everybody thinks, oh, the boundary gets maybe a little stronger, so maybe the curve does this, or it gets a little weaker, maybe the curve does that. But what it actually happens is when you do a different boundary conditions, you get a fundamentally different relation. And that's what that paper is about. Again, only read it if you're interested.
Professor?
Yeah?
What's the constant value on the first term on the left?
This one?
Yeah.
So that's the amount of hydrogen segregated to the boundary. So.
And the other is the chemical potential?
Yes, correct. So what I'm doing is juxtaposing the two conditions. Either you pull this boundary apart with a constant amount of hydrogen segregated to it. That's this derivative. Or you pull it apart, letting it at any time equilibrated with the hydrogen in the bulk. That's this derivative. That makes sense?
Yep.
Okay. I've noticed that I go much slower teaching this way, but that's okay. We'll figure out a way to deal with it later. Most of you are going like, God, I can't imagine the pace before. tell me if I need to go faster, if you're bored. I want to come back to the definition of properties before we do a few more derivations, just to sort of break it. I showed you the beginning of this before, that properties of materials are second derivatives of the potential. I just want to generalize this a little, right? So let me first do this for G, which is a function of T and P, if we have a simple system with only PV work, which means that temperature is the first equation of state. Sorry, entropy is the first equation of state. Entropy as a function of temperature and pressure, and volume as a function of temperature and pressure is the second equation of state. If you take the derivative, so if I take d squared G, dp squared, well, the first derivative is V, so this is dV dP, so that's compressibility. So this is minus V beta T. All right, give me a second. And then d squared G dt dP, so the cross derivative. This is dV dt, but it's also equal to minus ds dP, and so that's the thermal expansion. That's V times alpha V. So if I think of the matrix of second derivatives, I have minus Cp over T here. I have V alpha V here. That's the diagonal elements, and the off-diagonal elements are related by the Maxwell relations. Sorry, this is P. This is minus V beta T. And this is V alpha V. So the diagonal elements are the heat property, the mechanical property, and then the diagonal elements are the ones that combine them because they are thermal expansion. They're in some sense a change of the mechanical variable like volume with respect to the thermal conjugate. So these are the easy properties. Let's generalize this. To a system with more work variables, for example, a magnetic system. Let me actually come back to, for a moment to this. So what this tells you is that if you have only PDV work, there are only three relevant properties that define the system, right? Heat capacity, thermal expansion, and compressibility. That doesn't mean there aren't other properties of the system, but they can all be transformed into these. So I could make the matrix of second derivatives of the enthalpy, for example, or of the Helmholtz free energy, and the properties that show here would be slightly different, but in principle, you are able to calculate those properties in terms of these properties. So there's really only three independent properties. Okay. So for magnetic systems, now our du is TdS minus PdV plus mu naught H dm. I have an extra work term. Again, I'm going to mess with this and just drop the the mu naught into h, so I can just write h dm, and then remember that this is multiplied by volume, right? So it's not the magnetization from your electromagnetism course, which is a density. Here it's multiplied by volume. So I'm going to do a Legendre transform to the variables that I normally control, T, P, and applied field. So I'm going to define a G-like potential, right? So a G-like potential, which is U minus Ts plus PV minus HM. That's my Legendre transform. And the differential of that is going to be minus SDT plus VDP minus MDH. Okay, so now let's figure out what the properties are. So what are the properties of a system like this? So now I have 3 intensive variables. I have T, P, and H. The first ones, the ones with respect to T, will be the same, right? These are the same as before, except at constant H, right? So I'm not going to spend time on them now. But let's see what the new properties are, since some of them are kind of fun. Okay, so let's figure out what this one is. Temperature, free energy derivative with respect to temperature and H. So d squared G dt dH. What is that equal to? Okay, if I take the derivative with respect to temperature, I'm going to get entropy. So I'm going to get a derivative of the entropy with respect to H. So this is minus ds dH at constant T and P. And through the Maxwell relation, or I simply take the derivative in the other order, if I first take the G dH, I'm going to get M or dm, right? And so I have then dm dt. So this is also equal to minus dm dt at constant pressure and applied magnetic field. This is actually a physical property, but it actually usually doesn't get given a name nor a constant. But it's how magnetization changes with temperature. So very often we'll just list it as dm dt, but it is a property, like, you know, dv dt is thermal expansion. It's just that dm dt, we actually don't give a name. In magnetism, people have made laws from, right, like the Curie Law. The Curie Law is a law for how magnetization changes with temperature, but it is a property. So over here we get dm dt. So let's do another one. So let's do the one with pressure. So let's cross pressure with magnetism. Let's see what that's going to give us. So we get d squared G dP dH. Right? Pressure derivative is going to give us volume. So, or if I take first H, then I get dm dP. This is minus dm dP at constant H and T. And this is also equal to, if I first take the derivative with respect to pressure, I get volume. So I get the derivative of volume with respect to the applied magnetic field and at constant pressure and temperature. And that's a funny one, right? Is how volume changes when I apply a magnetic field. This has a name, it's called magnetostriction. And it's defined as gamma is 1 over V dV dH. I'm giving you the simple version of magnetostriction. Sorry, and it should be at constant P and T. In reality, in a crystal, gamma is a tensor, right? Because I've made volume here, I've made the system isotropic, but in principle, this could be linked in some direction, and this could be the applied field, right? In reality, the field is also a vector, but I've just treated it all isotropically, so there's only one magnetostriction. In a crystalline material, there will be many magnetostrictions, right? It's a crystallographic tensor. But here we're going to keep it simple, and there's just one magnetostriction. But it's a cool variable, right? It tells you how the volume of a material changes as I apply a magnetic field. By the way, this is one reason that transformers hum, right? Because when I apply a magnetic field to the iron core which is a bunch of lamella, right? When I apply a field, remember in a transformer, the field is switching whatever, 50 or 60, whatever frequency you're on, times per second, the volume slightly changes. So this is actually what causes hum. Okay, I'm running out of space here. So let's do the last property. Which is d squared g with respect to h and h again, right? It's the one that's going to come here. So d squared g dh squared. This is going to be minus dm dh. And dm dh, that's susceptibility, right? So this is going to define a magnetic susceptibility. And I'm going to define that as chi, again, normalized by volume, dm dh at constant temperature and pressure. So this is my magnetic susceptibility. Okay, so what appears in this matrix of second derivatives here, right? dt dh, so here I get minus dm dt, and I get that here too, right? Minus dm dt. When I cross mechanical things with magnetic field, I get the magnetostriction. So here I get V times gamma, and here I get V times gamma. And what do I get here? Here I get minus V times the susceptibility. And just to remind us what we got here, so here we got minus Cp over T. Here we got the compressibility minus V times beta T. Here we got V alpha V. I should move this here. So that's the property matrix for a magnetic system. I have this slight feeling I may have messed up a few signs, but I'll check them, and if I got them wrong, I'll correct them next time. So if you look at the diagonal elements, they are the properties that live within one field, right? Because they are the second derivatives with respect to twice the same variable. So heat capacity, right, comes out of thermal science. This is some mechanical variable, right? In our case, it's compressibility because we treat our system isotropically. But in general, you could have a whole submatrix here of elastic constants, right? Because this is mechanics with mechanics. This is magnetism with magnetism. So that gives you the intrinsic property of electromagnetism, which is susceptibility. But then the off-diagonal elements are the ones that combine the fields, right? So we got thermal expansion, right? That's combining mechanics or dimensions of a material with thermal. We got dm/dt, which combines magnetism with temperature. And then we got these sort of interesting ones, right, which combine mechanics with magnetism, and that's the magnetostriction. So you can keep on going, right? You can start dreaming like, you know, what if I added like, I don't know, what if I added electrical potential? I mean, first of all, okay, help me out here. What's going to happen on the, what's going to come on the diagonal? We've done this, right? That's going to be capacitance, right? Because what relates, you know, what's the intrinsic property of sort of electricity? What relates potential to electrical potential to charge? Here's going to be capacitance, right? But let's look at a few weird ones, right? Like what's going to cross pressure? So mechanics with electrical potential. What's going to appear there? What are the coefficients that relate mechanics, therefore sort of how big something is, right? And applied potential. Remember that you can also... I'm sorry, I think you said it right, but I didn't hear it.
Piezoelectric.
Yeah, so here are going to be the piezoelectric coefficients, right? They're the ones that relate electric fields to mechanics, right? I think I got them all, right? Did I forget any? Yeah. Oh, and then there's some weird ones, right? And we're going, what relates magnetism with electric fields? So I'll let you think about that. Oh, and there's another one. There's a cool one. We forgot this one. Temperature with electrical fields, right? That's what you use in sensors, right? Like you can, if you actually change the temperature in infrared sensors, you change the temperature locally through infrared, and that generates an electrical potential. So it's pretty cool how you can cross all these things. Let's see. What I'm going to do is end now, and then I want to show you a few examples of how you use these more complex properties. I'm also going to look through the signs because I have a feeling I may have been a little sloppy with the signs. I'm not sure they're all right, but I'll get that corrected for you if there's a problem with them. So, any questions? We have a few minutes for questions. Otherwise, you can have your morning coffee. Okay. Well then, good seeing you, and I'll see you again on Wednesday. See you then. Bye.